resistor that is being used or the minimum area that I can operate with. So for a given design, therefore, we define the metrics, and those metrics that we look for are typically VOL, okay, and VOH. So we said that if I have a chain of two inverters operating within the circuit, if I input 0, I will get the output being high, VOH, and if I input VDD, I will get the output being low, which is VOL, okay? And we said now, at the later stages in the circuit, I cannot anymore operate at 0 and VDD because the signal will propagate, the maximum value being VOH or the minimum value being VOL. And therefore, for inverter number 2, if the input is VOH, I will get VOL, and if the input is VOL, I'm going to get the output as VOH. So really, my input logic is really going to operate between VOL and VOH. And those values are going to translate to input logic 0 and input logic 1. Okay, but in reality, I want to define some noise margins. Yani not only when my input is VOL I can operate, probably my circuit can operate with some margin. And in practice, as we have learned in 310 and 311, once I hit the high gain region, once my slope of the voltage transfer characteristics becomes -1, at this point, this is where I declare, when dVo by dVin equal to -1, this is where I declare the limit to my logic 0 operation. So I define this point to be the input low, and we say that as long as my input is between VOL and VIL, I am still can assume that I'm operating as a logic 0. And in a similar fashion, if this was VOH here, then I can still accommodate inputs that are as low as VIH, which is also the point on the other side of the curve, yani moving further into the curve, where dVo by dVin equals to -1. So therefore, the logic 0 and the logic 1 are intervals defined by VOL and VIL, and defined by VIH and VOH. And we expect that the response of the circuit, for the logic 0 to give me something close to VOH here, and for the logic 1 to give me something close to VOL, or a very small range of fluctuation around VOL. Okay, so this is the definition of logic 0 and logic 1, and this range really determines my noise margin. So my noise margin high is really equal to VOH minus VIH, and my noise margin low is equal to VIL minus VOL. Okay, so these are my noise margins. Let us see now, as we proceed next, what we will see here. Sorry. Okay. So for robust circuits, to tolerate the noise, we want the logic 0 and the logic 1 intervals to be as large as possible. Yani we want this to be large and we want this to be large, because in between them we have an undefined region which can cause the circuit to fail, to be misinterpreted, and we don't want that much noise to be injected into the circuit. So the larger those ranges are, the more robust and tolerant to noise is my circuit. Great. So let us see how we can interpret this in a different way. And if a design has characteristics where it is robust to noise, okay, we will say that it has a regenerative property, and we will explain what we mean by regenerative next. Yeah, if you hit something and it comes back to its place, this is regenerative because it is able to recover. So not only we want the circuit to tolerate the noise margin, but also we want it to absorb it. Yani if the noise happens at this stage, we want the rest of the design to reduce it so that we do not see it towards the end. So we want a circuit that can recover and fix itself, not only accept a certain noise level and propagate it. So let us look at this example. Here we have VO has really a weak high and a weak low. Yani if the main value is 0 or VDD equal to 5, this is my 0, this is my VDD, well, this VO is operating somewhere between, let us say, 2 and 3 volts. So this is really a weak low. Yani let us assume that due to noise or some disturbance, I got here a weak low, so I had a weak low at VO or at V0. Okay, let us see how a regenerative or a recovering circuit works, and we will demonstrate why this happens on the next slide. V1, if you notice now, first of all, the range of VO, the range of VO is really small. Look at V1, which is the output. So V1 now, when VO is high, V1 is low. When VO is low, V1 is high. But the range of V1 is large. Look at the range of V1. So it's starting to recover the swing. It's now swinging, and it gave me closer to VDD. This is VDD, so now it's V high. Although this is a weak low, this has a good high now and a good swing, and now V2 in response to this good high all of a sudden recovered back to 0. So we can see that V2 here recovered back to 0. So the next stage, the good high, gave me an excellent low. Okay, so the weak low was inverted to a good high, which was inverted to an excellent low. So now you can see that signal V2 gives me a perfect 0 and a perfect 1, and it managed to recover from the small range here to a large range. This is what we call the regenerative property or the recovering property of the circuit. So it is not enough that my circuit has a good noise margin. I also wanted to regenerate or to recover properly. And let us see why this happens. This is good because this means my circuit can absorb the noise. Okay, so this means let us see now what happens here. Okay. So looking here into the circuit and looking at the distorted low at VO, this is inverter number 1, this is inverter number 1 characteristics, so this is V1 versus VO. We can see that if I start from a distorted low around here, okay, let us see what the animation will show me. I will get a decent high at V1, okay? So this decent high at V1, if now I look at the characteristics of inverter 2, which are shown here, the input is V1 and the output is V2, it is going to give me a low, yani I moved away from here by this much, and this is going to give me a low V2. So you're not supposed to understand how to follow the curves, but what I'm trying to tell you is because of this steep slope here, or because of the high gain region, the bad VO gave me a decent V1, and then the decent V1, because it happened now to fall in this low gain region, translated now to a good low. So to be regenerative, this is what matters really, is that the voltage transfer characteristics must have a transition region where the gain is greater than 1, surrounded by 2 regions where the gain is smaller than 1. يعني the transition region helps me flip between the 0 and the 1, and the small gain regions اللي هن within the noise margin regions allow me then to directly jump with the response to have a almost constant response for the range of the noisy input. يعني the slope here, the small slope, allows them all to be very low, and the transition region allows me to take a logic 0 into a decent high, even if it is distorted. Okay, so what we really need to take from this slide is that I need 2 low gain regions and in between them a high gain region. This is what matters for the regenerative property. Okay, طيب هلا great. So now they're just telling me, well, we've learned about all of this, but in real life or in practice, the noise margin really tells me how much I can overpower a noise source, but the real values can be deceptive. I'm going to ask you this question. Let us assume that I have a resistor connected to VDD and a capacitor here. Okay, and let us assume we inject some noise at this node. Okay, who will help the capacitor recover from this noise? What should be the ideal voltage here at this node? At infinity, where will the resistor take the capacitor?
VDD.
It will charge it to VDD, right? Now, if I pull it down with some noise or some coupling path, who will help it recover? Who will help it recover?
Power dissipated across the resistor.
Yes, so who will pull it up back to VDD if the noise was pulling it down? مين عم يمرق لها current على VDD?
The charged capacitor.
So the capacitor is here. It takes time to charge. Who is holding the node to VDD? The capacitor is a reservoir.
Resistor.
You throw
Resistor.
current into
Resistor.
it. صح. Okay. So the resistor is really what is connecting the node to VDD. So it will send current from VDD to recharge the capacitor when the noise goes away, right? يعني لو النويز سحب من الريزرفوار الريزستور حيرجع will charge it again, right? Based on its time constant. If now I have all of a sudden opened the link and let us say that this was VDD here, okay, or some source voltage here. I opened the switch and I had previously charged the capacitor. It was charged. And all of a sudden somebody pulls the charge through a noisy path or something, or it gets coupled or gets affected somehow. Will anybody, after the noise source goes away, after the noise withdraws current from the capacitor, will anybody charge the capacitor?
No.
No. So this we call it a floating node. Okay. So sometimes in dynamic logic or dynamic design, we charge a circuit, and if we let it float and we wait for some path to evaluate and pull it down. But if noise falsely pulls it down, then we might interpret it as an evaluate and we cannot recover from the noise. So this is why we are saying that noise margin is deceptive, because really there are floating nodes that are more susceptible to noise, and we need to know in what context we are operating. Okay, so these are all concepts that are new and fresh to you, but I'm just trying to fill in ideas so that as we study different circuits or different designs, let me just clear as we study different circuits or different designs, we can remember, oh, this is a floating node, it is not connected to VDD, it is not connected to ground, you know, and stuff like that. So what matters really is that, yes.
Can I ask a question?
Go ahead, please.
Why would we have these floating nodes? Is it by design?
Okay, we'll explain them later, but let me give you an example. Let us assume I'll just give you a high-level example, and later we will see it in real practice. Let us assume that I have a line, and in this line, I typically pre-charge it to VDD. Okay, so I'm pulling it with a PMOS, and then I turn this PMOS off. So the signal is low then high, right? And we will study this, okay? And I have some memory design that is connected during this. And let us say that this is the clock cycle. So this is when the clock is on. This memory circuit is supposed to evaluate, and if there is a match, it is supposed to discharge the capacitor. Okay, if there is no match, the capacitor will remain high. Simple logic function, forget how it works. We will learn very little basics later. If noise kicks in and I falsely discharge the capacitor, my system will think that when the clock was on, okay, the memory has discharged and therefore I have a match, and it's going to give another instruction, okay? So this is an example where we rely on discharging a capacitor to flag some event, and if noise falsely discharges it, it's a problem. Yani we leave the capacitor floating, and if there is an event, it will discharge it. Okay? But if the event does not exist, the capacitor will keep its charge alone. It's a floating still. There's no path to it, لا الVDD ولا الجراوند. فالنويز بيجي بيعطينا false alarm. Yes.
Thank you.
Okay, thank you. And please don't be confused by these. These are high-level concepts that we will learn them little step by little step. So let us just now worry about the concept. There is noise, there may be floating nodes, and I need to be able to recover, and I need to be able to suppress it. And there are different ways or different forms in which we suppress the noise. One of them is the ability of the circuit to absorb it and reduce it. Okay, طيب great. هلا directivity كمان is important. يعني if I have an inverter and I see a noise at this output, the noise can propagate forward, but definitely it cannot propagate backward. And this is why we design our gates to be unidirectional. When we study CMOS gates, I will remind you why what this means in terms of the basic inverter. ليش input does not propagate backward, it propagates forward. But the basic idea is that if you look at a transistor, right, the transistor is really the gate, or the gate is just a controlling element, right? And the current flows from the source to the drain. So any noise at this node is not going to express itself. It will affect everything connected to this node, but it does not affect the gate because the gate is insulated, right? So this is just the very basic, but we will study slowly the inverter, see where the transistors, how we can model them by the resistor, and from there it becomes simpler to you to understand why the gates are unidirectional. And people define output impedance and input impedance, but at this time I will not worry you about them. So let us look here at really, therefore, what's my ideal gate? The ideal inverter or the ideal gate will have infinite gain. It will, pardon me, it will have infinite gain. It will have zero gain here in those two regions. Okay, it will have the noise margin high and the noise margin low equal VDD over 2. ليش؟ لأنه هون عندها VIL equal VIH equal VDD over 2. So this is completely absorbs all kinds of noise. Okay, وعنده input resistance infinity because the gate passes no current. You know this, we're not going to need it, but we'll just explain it later. And it acts like a short circuit, so it connects the input, the output to VDD or ground, as we will study next. But what matters to us now is that noise margin high equal noise margin low equal VDD over 2. The gain is very large, and here the gain is 0. But also, an ideal inverter will be able to drive the signal to an infinite number of gates. يعني أنا إذا بدي أبعت signal, I can send it to as many gates as I want. Let me ask you this question. If you have a horse driving one carriage, or driving two carriages, or driving the signal to 10 carriages, which horse will be more tired and where the signal will become weaker? بالهorse driving 10 carriages, right? So
Yes.
this we call it fan out. يعني أنا how many people I can deliver the signal to allows me not to replicate things, right? So the ideal gate will have infinite fan out, but really this affects the delay, this affects the single transition, and therefore another concern beyond the noise is delay. And we start when we design the circuit to say, well, what is the number of load gates that each gate can tolerate? For example, in generation of, let us say in Power 7 at IBM, they say this library is fan out of 4, meaning a gate can drive at most 4 other gates. I cannot drive more. So we start to put constraints on the designers because gates with large fan out can be slower. And not only fan out matters, let us say later we will learn that, and you saw this in 3.11, that if I have A and B, I will need 2 NMOS transistors and 2 PMOS transistors, and the AND gate or the NAND gate will have 2 inputs. But if I want NAND of 4 inputs, I will have more transistors. So what we will review all of this slowly, but what we are learning is that fan-in is the number of inputs to the gate, but also gates with larger fan-in are bigger and slower. And we will show towards the end of the course, we will demonstrate how implementing a function with a smaller gates is better. For example, 2 stages, for example, A, B, and C, D, NAND. Implementing this as 2 gates is more efficient, or NOR in this case, is more efficient for me than implementing it using 1 big gate. And for this, all we will need is basic logic, logic thinking, and we will be able to proceed forward in these concepts. So this is just heads up.
Sorry.
Yes.
In the fan out example, so you're saying that the inverter's performance depends on current also?
The inverter performance, so what we will learn later is each one of these inverters will be some form of a capacitive load on my design. And if I want to send the signal A to many outputs, okay, and if I'm loading this inverter with many of them, the equivalent capacitance driven at this node is large. And really, what is this? This is a current source, right, which has an effective resistance, and it is in the end some resistor, right? Yep. So the equivalent circuit, which we will study later, will be an RC circuit. If you load it with many capacitors, this will be large, and the RC time constant will be very large.
Okay, thank you.
So we will explain all of these concepts later, but I'm going to talk today about the delay and about the RC time constant. Okay, so first, if I take it as a black box, the input waveform will result in an output waveform which has an inverted logic. Yani when this was low, this is high, when this is high, this is low, and so on and so forth. But what we care about is the 50% delay. Yani we are going to make a definition which is TP high to low. The definition really follows the output signal terminology. So the output is switching from high to low. So I'm measuring the delay TP high to low, and it is the delay from 50% of the input to 50% of the output. Okay, so this is the first delay term definition. The TP low to high is the delay or the time it takes the output to switch from low to high, and it is the time from 50% input to 50% output. Okay, so therefore we have the delay, but also we define the propagation delay as the average of TP high to low plus TP low to high. And we also define the rise time and the fall time of the signal. Okay, so signal itself, it is varying from 10% to 90%. Okay, so the signal is varying from 10% to 90% of the signal, and we measure the rise time of the signal. It matters as well. Okay, so all of these values can really be derived from a simple delay model. And this simple delay equivalent model, which we will be using a lot and explaining to you how we find it, is based on this simple RC time constant circuit. So the first order RC network, we rely on it to predict all of these delay points. Okay, so the first important metric is really the time constant tau, which is equal to RC. Okay, and if I have a signal feeding into a resistor going up, let us say to VDD, okay, then the capacitor is going to charge from 0 all the way to VDD at t equal infinity, right? So this is the voltage across the capacitor. So let us see how this equation is derived, okay? So the general rule, which you all know, is that V out or V cap of t is equal to V final plus V initial minus V final times e to the minus t over tau, right? And I know that if this is the voltage supply, which is stepped up, okay, that the capacitor will start initially from where? My capacitor is going to start initially from 0, and at infinity, the final value, for example, is VDT. So the equation, pardon me, the equation V out of t is equal to VDD plus, 0 minus VDD into e to the minus t over tau, and this becomes equal to VDD into 1 minus e minus t over tau, right? Great. Now, if I tell you, find for me the time t, if it started already at 0, at which V out is equal to VDD over 2, what do? You plug in.
Yes, we replace V out by VDD over 2. And,
in this equation, so you say VDD over 2 is equal to VDD into 1 minus e minus t over tau, right? And so this becomes half is equal 1 minus e t over tau. And we end up finding that t is equal to tau ln 2, which is the equation that we have here, which is 0.69 tau. So assuming that the switching happened at t equals 0, at t equal 0.69 tau, my output will reach the 50% point, and I can calculate my delay from this equation. Okay, now if we ask you, what is the rise time of this signal? How is it rising? And what is the rise time? Meaning the time it took it to go from 10% to 90%. How do we find that?
V out equal 90% VDD.
Exactly. So I need to solve for 0.9 VDD, right, equal to VDD into 1 minus e minus t over tau. And this gives me time t2 or t 90%. And I need to solve for 0.1 VDD. Exactly, into 1 minus e to the minus t over tau, and this will give me t 10%. and then the T rise is equal to T 90% minus T 10%. In this, just remember that if you have minus ln A, it's equal to ln A to the minus 1, right? And if you have ln A plus ln B, this is ln A times B, or ln A minus ln B, it's ln A over B. Okay, so just be aware of those equations here. And if we go back and look at the here, it ends up being ln 9 because of the difference, okay? And somehow, if you note, the 10% is responsible for the 9 and the 90% is responsible for the over 1. So just be careful and don't correlate it direct. Don't map it in your head when we solve directly. Make sure that you flow through the equations here. Okay, so I find the T 90%, I find the T 10%, I subtract them, I know my knowledge of logarithmic rules, I apply it, and I find the rise time. Anybody has a question? Okay, great.
Yes, Doctor,
Yes.
we always refer to the rise time as going from 10 to 90, or is there some instances
This
where
is
we
the
change
default
the
rule.
values?
This is the default rule.
Okay.
If a company is interested in 20 to 80%, they will tell you, find the time it took to go from 20 to 80%, right? So if we just say the rise time, then it is 10 to 90. Okay?
Okay, thank you.
Thank you. طيب, great. Now that we understood how to deal with the RC time constant, I'm going to explain a little thing. So when we have the chip design, typically every chip that is fabricated may be different from its sister chip, as we said, and the designers would be curious to try to characterize what is the delay or what is the clock frequency that should be used on each one of these chips. And in order to do that, if I want to put only one inverter that is not functioning, so this is the circuit, and they put some pilot cells which give them a hint about the functionality, which are quick to test. We cannot test using a regular workload. Typically, we put small piece of circuitry. Well, I cannot measure on the chip, let us say nanoseconds or picoseconds, okay? So what they do is they put some circuit element that generates a clock, which has a wide range. يعني مثلا let us T is a few nanoseconds or tens of nanoseconds, and they measure the oscillating frequency of the circuit. And if they find that, for example, this batch is fast, this batch is slow, then they start to divide them, the one that operates at 1 gigahertz, the one that operates at 2 gigahertz, and something of that sort. To build this, they really use inverters, just the very basic circuit. But let me ask you this question first. Let us say that I have an inverter and the input here is 0. What is the output here? 1. Okay, yeah. Great. Now I connect this to another inverter, back to back. They are even. The one here, what does it translate to?
0.
0. So this is a basic latch. If I store a 0 here, it will stay there forever because this one will preserve it. صح? One will carry the 0 and the 0 will carry a 1. So this is a basic latch. Let me ask you about this. If I have now 3 inverters, okay, the 0 here will be here what?
1.
1, and here?
0.
0, and here?
1.
1. It is shorted to a 0. So this is a ring oscillator. Okay, and this is going to generate my clock on the chip. Let us see what, 1 second, sorry. راحت السلايد كأنه I apologize. Okay, so let us look at the ring oscillator circuit here. So I'm going to follow the same logic with you and start to draw the signal. So I started with a 0. I have a 1 here. I will have a 0 here. I will have a 1 here, a 0 here, a 1 here. I have an odd number of inverters. So let me see what is going to happen. This means that let us start counting. Okay, so at this time, when the fifth inverter became a 1, I had at this node a switch from 0 to 1, right? At this time point, أول ما وصلت ال1 لهون, I had a 1 here. So my signal flipped from a 0 to a 1. Now let me assume that each one of these inverters has a delay TP. Okay. What is the distance from here to here? 5 delays, 5 TPs. So after 1 TP, this one becomes a 0. My output is still the same. Okay. Second TP, this 0 becomes a 1. My output is still the same. The third TP, this becomes a 0. My output at this node is still the same. The fourth TP, okay, هيدي قلبت ل1. The fifth TP, هيدي قلبت لقد ايه؟ 0. صح? So this node now became what? This node becomes a 0. So أنا نزلت رجعت على 0. How much time did it take me? 5 TP. عدد the stages of the inverters that I can see here, right? So 5 TP. Now let us start counting again. So this is the first TP, the 0 will propagate, give me a 1. This is the second TP, this will propagate, will give me a 0. The third TP, this will become a 1. Fourth TP, 0. Fifth TP, 1. So again, after 5 TP, I flip back to what? 1. What is the period of this clock?
10 TP. لا, this drop only 5 TP.
The period of the clock كلها. يعني من
clock.
أول رايز
10 TP.
10 TP.
تاني رايز هذه 10 TP. Okay. فإذا really the basics of the string oscillator is that I need to have an odd number of inverters, صح? And the period T is going to be equal to 2 times the number of inverters times the delay of the single inverter. Right? So if the delay of the inverter is 50 picoseconds and I don't have equipment to measure it, I can put a chain of 200 or whatever number of inverters, or 201, and then I will get a period which is in nanoseconds, and then I can measure it externally to understand what's the frequency and know if this chip is a fast chip or a slow chip, etc., etc. Now, the same that we see at node 0, it is really fluctuating up and down. Also, the other nodes, any other node inside this ring oscillator V1 or node 2 or node 3 or node 4 will really also be oscillating, but it will be delayed by one inverter. Yani if this node rises at this time, the other one will be rising one stage after it. The fourth one will be rising 4 stages after it. يعني هن shifted في بيناتهم TP delays based on the number of inverters, but they all will oscillate. Each one of them will oscillate with a period equal to 2n times TP, but the edge of their clocks are delayed based on the number of inverters between them. Anybody has any question?
Professor?
Yes.
ليش بس عم نفوت على الفيرست انفرتر وعم ننقل من 0 ل 1 و 1 ل 0 عم نضلنا على ال 1 بالريد drawing تحت.
Let me explain it again. 1 second. So let me just duplicate it. Okay. So let us see what is happening. This is the node that I am reading, right? That was 0. Sorry, خلينا نبلش فيها. بالأول هاي النود شو كانت؟ 0 صح؟ يعني I had a 0 here, it had a 1 0 1 0 وقلبتها لل1 صح؟ So أنا if I'm reading this node هيدي النود بس حاطة مونيتور عليها هلا قلبت لل1 صح؟
Yes.
قديش بدي لأقدر أوصل لهون distance؟ ما أنا هلا
أوكي.
صاروا مثل بعضهم الشورت مرق لي إياها لحتى هول باقيين يتغيروا يعملوا الدومينو افكت شو عم بيصير ال1 عم تقلب مين؟ 0
الزيرو.
تغيرت هاي بعد؟ Did this change yet? Did this change yet?
أوكي.
لا امتى هي بتتغير؟ لما هيدا حيغير هيدا حيغير هيدا حيغير هيدا سو بده وقت الدومينو تريبل صح؟
Yes.
الزيرو حتقلب ل1 ال1 حتقلب ل0 الزيرو حتقلب ل1 لهي بدورة تقدر ترد هاي زيرو هيدي الريبل افكت effective immediate يعني نحن النزلة أو الطلعة هيدا switching is because of the short it is effective immediate but for this location to flip I needed to have rippled or dominoed effect through all the 4 transistors the inverters 5 inverters right
Yes.
okay so this is why this is happening يعني بس تقلب هون حتجي ظهري as input وتغير بس حتدلها هالقد لعند ما هال change propagates و translates to the next value.
اوكي مشان هيك لانه we're monitoring على الاول مشان هيك ما الترانزستورز اللي بالنص ما بيأثروا على انه على الساين.
لا هن حيقلبوا exactly هن زي are fluctuating بس انا I'm reading this node هي تغيرت لتغير كل اللي بعدها لعند الانبوت directly before it وهو ياخد وقته ليقلبها لأنا أقدر أشوف التشينج وهالشي بياخد length of 5 inverters. Okay?
Thank you, Professor.
Okay, you're welcome. Anybody has any other question? Yes.
Yes.
Professor, قد ايه بيفرق قد ايه في margin إنه يفرق ال TP from one inverter to the other?
Yes, there is variability. So this is why we say that we take large number chain. So if this chain is say 200 inverters, so the top population based on the law of large number, if I have a very large number, their delay will be what? N times the average TP, right? يعني if one inverter is weak, one is slow, one is bad, one is good, they will average out to some average expected value, and I can know on average my chip is behaving properly or not. يعني قديش هي سرعتها on average, okay?
Professor, this changes over time?
Yes, there is aging effect on chips that can be translated to delay variation, and this is why also the string oscillators are good monitors. ولهيك بيحطوا شيء بيسموهم canary cells يعني مثل المراسيل أو birds that tell me the activity of the chip and how it is aging and stuff like that. So these are all good indicators for monitoring the chip behavior. Yes. Okay.
Thank you, Professor.
Okay, thank you very much.
Professor?
Yes.
Is it of any use أو في شيء design that adds another branch of inverters, a series of inverters to this؟ يعني بعد أول inverters تعمل branching ل another series of inverters
Your
that are parallel
oscillator will be
لأول
complex. Your oscillator will be a bit complex. Typically, ring oscillators are designed to be simple. People have designed complex ring oscillators, but we just want to understand the frequency of operation, and we use this to create a clock from it. Okay?
Thank you.
Thank you. Okay. Right, let me finish the last slide on this sheet so we can start the new set next time. So from another concern, in addition to the delay, is the power and energy dissipation. Why do I worry about power? The peak power, if you know, you are all familiar with the disjoncteur of electricity where we have to switch it, and if we overload it, it really breaks. The reason it breaks is that the wire that we put to connect between the source and our house is thin enough that if the current increases beyond a certain voltage, beyond a certain value, pardon me, it will break, right? So in a similar fashion, when we are studying the design, we care about the peak power, because the peak power is really, P peak is VDD times I peak. And it really matters for us to determine the supply line sizing, and how much metal I should use for a robust supply, so it can handle the peak current that is drawn by the chip. And typically, although peak current does not affect the battery lifetime, but it really affects the reliability and the ability of the supply lines to be delivered to the gates without burning. So peak power is a concern. The average power, which is 1/T integral of VDD times IDD of T, determines for me the lifetime of the battery. And in the end, the battery is a reservoir. It has a fixed amount of energy it can deliver, and the average power tells me what is the lifetime of my battery. And of course, from a power perspective, hydraulical and high-level concerns that we are talking about, we care about proper packaging and proper cooling. حتى ما يصير overheating, حتى ما يصير في metal wires shapes will change, and even in some extreme cases, the chip will burn. So these are the concerns in this course. What we care about are two components: the dynamic power and the static power. Dynamic power is the charging and discharging of the capacitors, and in some cases the short circuit current. And the static power is independent of the switching activity. It means whether my circuit, when it is stable, not switching logic, not changing evaluating functions, if it really dissipates power, this can be costly for us in terms of operating and in terms of the battery lifetime. Okay, so these are the main concerns that we will have hopefully a good overview during the course of the semester. And to summarize, integrated circuits have really advanced and have very good potential to keep going on, and they have brought many new innovations. And there are certain challenges that we need to worry about, and we need to mainly understand the cost, the reliability, speed, power, and all of these design metrics that govern today's digital design. Okay, so I will conclude this session here, and next time we will start talking about the MOSFET as a basic structure and as a switch, as a logic element that fluctuates between 0 and on and off, or a switch that fluctuates between 0 and off. Okay, thank you all, and we'll catch up next time, inshallah. Okay, goodbye, take care. Bye.
Thank you, Professor.
Professor, can I ask you?
Yes, go ahead.
Yes. Can you please go back to the ring oscillator slide?
Yes. Let me share again. 1 second. Yeah. Okay.
Yeah, sorry for the trouble.
No problem, no problem. بس كنت عم أتأكد إنه الريكوردينج ماشي، لأنه شفته وقفته أنا بالغلط يمكن. Okay. So let me share the screen again. Okay.
Yeah, so there is something that I did not understand. We're saying that it's initially it's a 1 or a 0, it depends, and then it becomes it flips after 5 delay times. But all the while V0 is decreasing gradually.
Let me explain to you what is happening one more time. 1 second. What is happening here is the following. If you look at it, شو عم بيصير? At T0, right? So let us assume that there was a switch. Let me assume that this was not connected, that somehow this was not connected. Okay? and I had somebody driving this node to 0. Okay, هيدا كان open. Okay, طب هيدي 0. What happens here? 0 شو بتعطيني هون؟
1
1 0
0 1 yes
1 0 وهيدي مفروض هون 1 and
Yes.
this was driven by another source somehow حدا شغل لي إياه. Now let us say that at the same time point where I remove this I close this switch. هيدا as a short circuit صح؟
true
What will happen to this node?
1
1 so أنا بلحظة سريعة قلبت من الزيرو لل1 على أي نود عم نحكي على VO.
Mhm.
Okay, and this is the time scale. Now, this one after a delay TP is going to flip V1 to become what?
0
0. تغيرت هون شيء؟ هيدي بعدها شو؟
yes بدنا ننطر لل V5 تصير
بدنا ننطر لهي تقلب ل1 هي تقلب ل0 هي
Yeah.
تقلب ل1 لهيدي تقلب لشو؟ ل0.
لا 0 yes
So what
Yes.
was your question?
that I understand بس أنا اللي يعني الجراف لأنه V0 is decreasing gradually مش abruptly ف
هلا طبعا in the end when it is oscillating ما هيدي الجراديوال منين عم تجي؟ من هيدا الترانزيشن ما هو هيدي هي وعم تطلع this is going to go down. It will not become 0 perfect. It's not decreasing gradually because of the short circuit. It's decreasing gradually because it is the output of an inverter that has some time constant, right?
okay
Embedded in it. يعني this is because of the behavior of the circuit. وكلهم
Yes.
حيكونوا هيك. هاي لما بتطلع حتطلع على مهلة وهي لما بتنزل تنزل على مهلة. ما فيها تعمل direct flipping. Okay.
deal thank you